Hi everyone, and welcome to the first of the Quantitative Data Analysis module lecture videos. So over the course of the semester, you've learned about different ways to collect quantitative data, but today I want to focus on the next step, analyzing that data so that you can make conclusions from your research study. Let's get started. The simplest way to learn about the data contained within a variable is to use what's known as a frequency distribution. Frequency is simply a fancy word that means the number of times each option was chosen in the sample. To calculate frequency, all you have to do is count up the number of times each option was selected, and there you go, you have its frequency. Frequency is abbreviated to a lowercase italicized f, so if you see that in the formula, you know what that means. Now, frequency distributions can be portrayed using tables or graphs. In this lecture video, we'll talk specifically about tables, but I want to show you about tables and graphs as well. So for example, let's say I had a closed-ended survey question that asked the respondents, what's your favorite color? Respondents were given a choice between red, blue, or other. Using the frequency table shown here, we can determine that 3 people picked blue, 6 people picked red, and 1 person picked other. That means there were a total of 10 responses. We can also display our frequency distribution in a graph. This type of depiction allows for quick and easy comparisons between the 3 groups. Now here's the problem with simple frequency statistics. Frequency values only work when you're comparing equal sample sizes. For example, here we can make a direct comparison between sample 1 and sample 2, clearly identifying that there are more individuals that identify as Asians in sample 2 compared to sample 1. However, if we look at another sample, we have issues with sample sizes. Sample 1 and 2 both have 100 people, but sample 3 only has 50 people. So now that easy comparison isn't valid. How do I compare the number of Asians in both samples if I do not have equal sample sizes? When you have unequal sample sizes, we must use a standardized value for all comparisons. A standardized value means that the value takes the sample size of the specific sample into account. That way you can compare unequal sample sizes That way you can compare unequal sample sizes easily. There are 2 major standardized values that you see in univariate analysis: proportion and percentage. Proportion requires you to take a specific value in each cell, the f sub I, and divide by the total sample size, which is capital N. Proportions will always be between 0 and 1.0. Now, most people don't like to interpret proportions, so we generally take the proportion calculation one step further and times by 100. This gives us a percentage from 0 to 100%, which is a lot easier for us to understand. So let's go back to that example of sample 1 and sample 3. Here I have 3 columns for each sample: the original frequency, the proportion, and the percentage. I've used the subscripts 1 and 3 to identify all of these statistics so that you associate them with the correct sample number. For the first cell, we'll take 50 divided by 100 because there are 50 people in that sample that identify as Caucasian and 100 people total in the sample. On the second row, we take 25 and divide by 100 because there are 25 people in the sample that identify as Black and 100 people in the sample, so on and so forth until we get to the total column. To double check my answers, I've added up all the proportion values and I get 1.0, which is the maximum value of a proportion statistic. Now, because of rounding issues, you may see this value go from 0.9 to 1.1, and that's okay. We do the same thing for the third sample, but this time we divide all the frequencies by 50 since that's the total sample size of sample 3. That gives the proportion values you see here. I add up all my proportions to double check, and I still get 1.0, so I'm good to go. Now that I have my proportions, I just need one thing to get my percentages, times each value by 100. So I take 0.5 and times by 100 to get 50%, 0.25 by 100 to get 25%, so on and so forth. Add them all up and I get 100%, which is my maximum value for percentages, again, so I'm good to go. Remember that this could be off slightly as well, so you can get 101% due to rounding errors. Oh, there's my 100%. And I'm going to do that same part for sample number 3. Okay, so I've cleaned up the table because that was a lot of math on there and it was probably making some of your head spin. So this looks a lot nicer. Same numbers, just no math. So now let's take it back to my original question. How does the number of Asians in sample 1 compare to the number of Asians in sample 3? I'm going to use the percentage column because that's my preferred standardized value, but you can use proportions or percentages to answer this question. When I look at the standardized values in sample 1 and 3 for Asians, I see there is a difference. Even though the plain frequency values were the same, the different size of the sample mean that Asians have a much stronger representation in the third sample as compared to the first. So I would say these are not equal distributions. So far, we've dealt with frequencies of only a single variable, but often we want to compare two different variables, such as our independent and our dependent variables across groups. For that purpose, we use what's called a bivariate table. Bi meaning there are two variables in the table. The bivariate table allows us to compare the frequency distribution across two different variables simultaneously. The rules for bivariate tables differ between disciplines, but in the social science world, our rule of thumb is to always put the dependent variable across the rows and the independent variable options down the columns. We then use column percentages to analyze the distributions. Let's do an example so you can see what I mean by that. In this example, we're looking at the victim-offender relationship and victim gender in U.S. homicides. We know from the rule of thumb that the labels going across the top of each column are the independent variable options, male victim and female victim. So our independent variable is victim sex. The same rule of thumb tells us that the labels going down the first row are our dependent variable, intimate, family, acquaintance, and stranger. So our dependent variable is victim-offender relationship. There are two ways to interpret a bivariate table that can help us analyze our dependent and our independent variables. The first is called marginal totals. A bivariate table contains the basic frequency distribution of the independent and the dependent variable by themselves in these marginal total areas. So even with a bivariate table, we can still analyze the distribution of each variable by itself. The independent variable frequency distribution is obtained by adding up all of the values in each column to find a column total. The bottom row now represents a frequency table of victim sex only, 11,412 male victims and 3,335 female victims. The dependent variable frequency is obtained by adding up all the values across each row to find a row total. The last column now represents a frequency table of victim to offender relationships only. Now we know that regardless of victim type, there are 1,969 people killed by intimate partners, 1,915 people killed by family members, and so on. The final number in the chart is the total sample size, or the table total. In this case, we are looking at a total of 14,747 homicides in the table. The second way to interpret our bivariate tables is to use column percentages to compare the dependent variable values across our independent variable categories. Column percentages work the same way as the percentages that we previously calculated. The only difference is that you use the total n for each column rather than the total n for the sample size when doing the calculation. For example, if I wanted to know whether male victims have the same victim-offender relationship with their killers as female victims do, I would use column percentages to compare the distribution of relationships across both types of victim columns. The problem with the chart is that as written, there are many more male victims than female victims, so we can't compare raw frequencies. Remember that percentages are standardized values that allow us to compare distributions between uneven groups. So I want to translate this table into column percentages so that I can answer my research question. To do that, I would take each frequency value, divide the column total, and then multiply by 100. When you're calculating the percentage of male victims that are killed by an intimate partner, you would use 496 as the frequency value and 11,412 as the column total. Dividing those and multiplying by 100 gives us a column percentage of 4.35%. I do the same thing for female victims, and I find that 44.17% of females killed were killed by someone who was in an intimate relationship with them. So now this type of standardized percentage allows us to compare both columns to one another. Here's the entire table converted into column percentages for analysis. You can tell I use column percentages because the last row is made up of all 100%. Now that I've standardized the values, we can make statements about our research question. Do male victims have the same victim-offender relationship with their killer as female victims do? Looking at the column percentages, we can see that over 50% of male victims are murdered by an acquaintance, but only 27% of female victims are murdered by an acquaintance. Instead, the most common victim-offender relationship for female victims is intimate partners. So no, female and male victims do not typically have the same relationship with their killers as one another. All right, well, that's all for the frequency tables lecture. Thanks for watching, everyone.